right, welcome everybody. Wanted to talk to you briefly here about the methods that Aristarchus used to measure the distance to and the size of the sun, so the star at the center of our solar system. Just to put the circumstances of this measurement into context, just wanted to remind you of a few things from the timeline we had before. Aristarchus was active kind of in the mid-200s BC, and this would place him about 100 years after Aristotle. So he did already have access to and had read and was quite familiar with all of Aristotle's thoughts on physics, all of Aristotle's thoughts on astronomy. He had inherited from Aristotle the conviction that the Earth was almost certainly a sphere, and he was aware of all of Aristotle's what would turn out to be mistaken predictions about physics. Now, did Aristarchus know that these were mistakes? Well, not entirely, although as we did say, he was the almost unique in this era of history in rejecting Aristotle's idea that the Earth was a stationary ball at the center of the universe, and in favoring the idea that the Earth orbited the sun. So more on that in a little bit. But around that same time, BC 250, Aristarchus was a contemporary of another gentleman whose work we've discussed before and was a subject of that Carl Sagan video we showed. This would be Eratosthenes. And for the purpose of, Eratosthenes actually had a great number of accomplishments in a long and fascinating life, but for the purpose of the conversation we're having right now, Eratosthenes' most relevant accomplishment was he was the one who had measured the shape and size of the Earth. So he had confirmed that, yes, as Aristotle thought, the Earth is a sphere. He had measured that it was about 25,000 miles in circumference, or another way of putting that would be about 8,000 miles in diameter. Eratosthenes had not done anything to radically shape up the question of whether the Earth is the center of the universe or whether the Earth orbits the sun. Presumably Eratosthenes, like most people at the time, agreed with Aristotle that the Earth must be the center of the universe. Nothing in Eratosthenes' methods for measuring the size of the Earth really depended on the answer to that question. So you could be wrong about the position of the Earth in the universe and still do a perfectly accurate job of measuring its size and shape, which Eratosthenes apparently did. Now, by the time Aristarchus made the measurement we're going to talk about today, he was already aware of Eratosthenes' work, so he knew that the Earth was about 8,000 miles in diameter. He also knew something that we've talked about in class, which was Aristarchus's first important astronomical measurement was he had already measured the size and the distance to the moon. You might remember he measured the size of the moon by seeing how many moons could you sneak inside Earth's shadow during a lunar eclipse, and deduce the distance from the fact that, well, you know how big the moon looks on the sky. It looks about half the width of your fingernail at arm's length, or it takes about half a degree of arc. If you know how big the moon really is, and you know how big it looks, you can work out from simple geometry how far away the moon is. So Aristarchus had found that measurement as well, and what he got for that was that the distance from the center of the Earth to the center of the moon is right around 250,000 miles, right around 250,000 miles. Would have been using the units of stadia back in the day, so that would be more like 2.5 million stadia, but units are units. But he had the distance pretty much perfectly correct. And Eratosthenes had the size of the Earth pretty much perfectly correct. So they were starting from a background where they had some pretty good measurements already. Now, Aristarchus now said he was going to try something more ambitious. He wanted to measure the distance not to the moon, but to the sun. Now, up until now, in a lot of these exercises we've done as we try to discuss these measurements, we have made the approximation that the sun is almost infinitely far away from the Earth. Why was that an important approximation? Because it allows us to draw that the sun's rays as they fall on the Earth and as they fell on the Earth during Eratosthenes' wanderings from the city of Alexandria to the city of Syene, that the sun's rays are coming in almost perfectly parallel. Well, yeah, they are. The sun is far enough away from the Earth that if you wander 500 miles across the surface of the Earth, it's gonna turn out, spoiler alert, but they didn't know this yet because Aristarchus is still trying to measure it, it's gonna turn out that the sun is more like 100 million miles away from the Earth So to compare to that, 500 miles, that's nothing. So the sun's rays are coming in almost perfectly parallel to strike the surface of the Earth. Well, here we're going to be a little bit more ambitious. We're going to ask the question, can we approximate the sun's rays as coming in perfectly parallel as they hit this whole Earth-Moon system? We're no longer talking about wandering 500 miles. We're talking about wandering a distance of 250,000 miles. Is the sun still far enough away that we can approximate its rays as parallel? Well, Aristarchus knew that the answer was, at least that's got to be a decent approximation. If the sun was right up close, like it was here or something like that, that would mess up their understanding of the phases of the moon. That pattern of phases that you get during each 28-day lunar month, where the moon goes from new moon through half full, through full moon, back to half, back to new moon. The regularity of those phases, the fact that you see the steady progression of the shadow line across the face of the Earth during the month, that means that the sun's got to be far enough away that at least these rays are approximately parallel. It's not right in here, or you'd see a very radically different set of moon phases each month. So we start with that approximation that the sun's rays are coming in more or less parallel, but we're going to try to put the challenge to ourselves. Can we prove they're not perfectly parallel? And can we use that to figure out, okay, the sun's not really infinitely far away from this Earth-Moon system, but it's just a kind of a decent distance away. Now, through this whole conversation, we are not going to need to take an opinion on whether the Earth is the center of the solar system or whether the Earth orbits the sun. The geometry of measuring the distance to the sun can be carried out regardless of where you stand on that deeper, more fundamental question. All right, how did Aristarchus set out to measure that distance? Well, he realized, okay, I mentioned to you already that it is the fact that the sun's rays light up only half the surface of the moon at any given moment. This is why the moon seems to go through its array of phases every month as seen by Earth. In particular, at this moment when the moon is in between the Earth and the sun, which is the moment during the month when there would be the possibility of having a solar eclipse. Now again, it doesn't happen every month. Why not? It looks like it should happen every month. The moon should go between the Earth and the sun every month. But again, remember, first off, the moon's a lot farther away than I've drawn it here to scale. 8,000 miles compared to 250,000 miles, that's about a factor of 30, a little more than 30. So I should go a little more than 30 Earth diameters out before I draw the moon's orbit. Instead, I went 3 or 4 Earth diameters out. So the moon's orbit's much more distant than I've drawn it here. And because of that, the second fact that the Earth-Moon sun system is not a perfect two-dimensional whiteboard like I've got here, but it exists in 3 dimensions. So on a given month, the moon very often is a little bit out of the whiteboard on this side, or a little bit behind the whiteboard over there, and the moon's shadow misses the Earth. But again, every month you do get this new moon phase where a human being who's standing on the Earth, if they are looking up at the moon, they're going to see just a dark disk. There's still a lit up side of the moon, but it's the side that this person can't see. She's standing on the wrong side of it. Conversely, 14 days later, as the moon continues to orbit the Earth, our same observer standing on this side, she'll look up at the moon, and this time she sees it fully lit up because the sun's rays are coming from this way. The moon surface reflects the sun's rays. And again, you could say, well, she won't see it fully lit up. She'll actually see it totally in darkness because the Earth's shadow is going to hide the moon at that moment. That would be a description of a lunar eclipse. And again, they happen, reasonably often, but most months they do not happen because most months the orbits don't quite line up perfectly and the moon just slightly misses the Earth's shadows, a little bit on this side of the board or a little bit behind the board. All right, but Aristarchus said all that's well and good. I want to focus on this moment in the orbit. Now, what would this be in terms of the phases of the moon? Well, sun's rays are still coming from this way. They are lighting up half the moon, leaving half the moon dark like that. What does our astronomer standing here on Earth see now as they look up at the moon? They're going to see a perfect half moon. Moon will seem to be a disk in the sky, and exactly half of that disk is going to be lit up. The camera thinks I just made a little heart symbol. It was showing me cartoon hearts. I don't know if you can see that on your end or if it's just an Easter egg in the program I'm using. But that was very cute, program. That's not doing it again. But okay. The moon would appear to be exactly half lit up at this moment. Now, Aristarchus said, okay, I can take advantage of that. First off, I want to be really careful here. I don't want to just say, hey, yeah, the moon's about half full today. He said, I want to try to find the exact night, better yet, the exact hour. If I could get it down to the exact second, I would, when the moon seems to be exactly 50-50 split between light and darkness. Why did he want that? Well, because that would mean that the sun's rays coming from stage right here would be making a perfect 90-degree angle to his line of sight. So he said, here I am standing on the earth, I'm looking up at the moon, there's the sun's rays hitting the moon, and if the moon is exactly half lit up from my perspective, then that angle should be exactly 90 degrees. Okay, well, what does that tell him about the distance to the sun? Well, you can say at the same time, suppose the sun does turn out to be infinitely distant. And again, that doesn't have to really mean infinity, but suppose the sun does turn out to be so distant that he has no realistic chance of measuring that distance with this experiment. Well then, the sun's rays would be coming in perfectly parallel to one another, which means if this sun's ray up here hit the moon at a 90-degree angle to Aristarchus' line of sight, then this ray, which would be reaching Aristarchus himself, would also be at a 90-degree angle to that line of sight, because the two rays would be parallel to each other. So he said, okay, here's the plan. I am going to train myself to perfectly judge that half moon as close as I can, get the exact hour when it's exactly half full, and then, now assuming the sun is above the horizon, if the sun's not above the horizon at that moment, if it turns out the moon's up there and it's half full, but it's dark because the sun's below the horizon, well, then you'll have to wait 2 weeks because then down here the sun will be above the horizon when that happens. But suppose we get lucky the first time. So if the sun's above the horizon, the sun's rays hit the moon half full, the sun's rays are reaching Aristarchus, and then he has to kind of juggle a bunch of piece of strings or something like that. Say, okay, here's a string which is heading out toward my line of sight to the moon, and here's another string heading out toward my line of sight to the sun. Ah, shit, the sun's really bright. Assuming he doesn't burn his eyes out for this, the luckiest thing would be if the sun's kind of close to the horizon so you can observe it without too much eye damage. But you can see this is kind of a hectic experiment here, and shit, the clock is running. You got to do this at that exact moment when you think the moon's as close to half full as possible. It's not the easiest experiment, but if you pull it off, and if you find that this also seems to be a 90-degree angle or so close to a 90-degree angle that you can't measure the difference, then that just means the sun must be vastly far away. Well, that would be kind of a cool result in itself, knowing that the sun is vastly far away, but Aristarchus was kind of hoping that, no, this won't be a perfect 90-degree angle. It's got to be close, or we would have noticed the moon's phases would be all messed up. But it doesn't have to be perfect. Well, what if, now I'm going to exaggerate it a little bit. What if the sun is not infinitely far away? In fact, what if the sun is right there? I mean, I know it's not right there on this diagram, or it would be messing up the moon's phases again, but I want to investigate what would happen to this angle if the sun is not infinitely distant. Well, the sun would still have to be sending out rays that would hit the moon at that 90-degree angle to Aristarchus' line of sight. That would be why he still sees that perfect half moon up there. But what would be this angle? Well, the sun would be sending out rays that would reach our intrepid astronomer down there, and he would measure this angle right here, and it's not going to be 90 degrees. It's going to be less than 90 degrees. I mean, if the sun's really as close as I've drawn it here, that looks like that might be like a 70-degree angle. Well, no, it's going to be closer to 90 than that, but as I move the sun back farther away along this line, this angle is going to get closer and closer to 90 degrees. But if this angle is not quite 90 degrees, well then Aristarchus or any other mathematician of the time would be able to triangulate. You'll say, okay, let's do the geometry. Let's trace this line back. Let's trace this line back at that not quite 90-degree angle, and let's see where the two lines meet. And at whatever point they meet, that tells you where the sun is. That tells you how far away the sun is. Now, hey, maybe the experiment's gonna not exactly fail, but maybe it's not gonna give you a distance. Maybe it's just gonna, nah, this was so close to 90 degrees that I gotta just say the sun's vastly far away. Well, okay, Aristarchus may have fallen victim to a little bit of wishful thinking here, because in reality, this angle would be something like, well, let's see, the sun's 400. This angle would be like 89.8 or 89.9 degrees. And with the methods they had, especially since you're having to make this measurement at this ephemeral moment when the moon's half full and the sun's not burning your eyes, and all, it would be very hard to measure that angle was 89.9 degrees and wasn't 90 degrees. So probably there was no way to pull this off with the technology of the time. You'd still get an interesting result. You just get that the sun must be vastly far away. And that's a cool result in itself. However, Aristarchus was kind of hoping for a number. And maybe he did subconsciously fudge his numbers a little bit. Measure it looks like 90 degrees. Ah, shit. Well, maybe I messed it up. Look, measure it again. Looks like 90 degrees. Ah, shit. Maybe I messed it up. Measure it again. Looks like 87 degrees. That must be the right one. That must be the right one. In any case, Aristarchus in his early measurements measured this to be, I'm going to put a thought bubble on Aristarchus here because this isn't the right answer, but this is the answer he thought he had gotten. He got it to be about 87 degrees. Okay, no problem. You work your way through from that. That would end up meaning the moon was about 5 billion miles away when you trace those lines back. Now, sorry, not the moon. That would end up meaning the sun, I apologize, is about 5 billion miles away. Now, he then repeated the measurements. Now, a lot of the books he wrote about this, we only have partial copies, or we've got an early draft and not a later draft, but not vice versa. We really wish the Library of Alexandria had been a more fireproof repertoire of knowledge there. But from what we can piece together, he repeated the measurement and he got closer to 90 degrees, which is good. He's getting close to the right answer. The next time he did this, he got something like 88.5 degrees a few years later. That would put the sun about 10 million miles away from the Earth. What's the real answer? The real answer is that the sun is about 100 million miles away from the Earth, because the real answer is that this angle should be about 89.8, 89.9, somewhere in there, very close to 90 degrees. And again, probably he did not have accurate enough instruments to have been able to pull off that exact measurement. But so what did he get? Well, he published this result, and well, I've told you before, some of Aristarchus's other ideas were considered radical and foolish. In particular, the fact that he was almost the only one of that time and place who thought the sun was the center of our solar system and the Earth was orbiting the sun. Well, a lot of people thought he was a lunatic. Well, no pun intended, since the root of that word is moon. But a lot of people thought that he was suspected of harboring irrational ideas when he said the sun was the center of the solar system. Of course, the sun is the center of the solar system. But at the same time, they did respect his measurement acumen here. I mean, he laid out the methods. The methods seemed to work. Nobody else could do better than him at measuring that angle right there. So they accepted this measurement, and for literally centuries, verging on into thousands of years after this, nobody had a better measurement of the distance to the sun. It was not until after Isaac Newton, it was not until about the year 1700, that they finally sorted this out and fixed this measurement. Hey, I gotta tell you, this bugs me a little bit. Because in any world that I can understand, nerds love to check things for themselves, to repeat a measure. Even if somebody else has already measured something, you want to do it yourself. You want to show it to your students. You want to discuss it with your fellow nerds. Apparently, that was not the way the scientific community was thinking for large swaths of the past. They were kind of content to say, well, no, this has already been measured. I got to tell you, I mean, from BC 250 to AD 1700, there had been huge advances in instrumentation. They could have done a much better version of this. Tycho Brahe, who we will talk about this week in lecture, Tycho Brahe had the instruments where he could have nailed this measurement. He didn't bother to try because Aristarchus had already measured it, and we already knew the answer. That odd lack of curiosity or lack of drive to check for yourself something you already know, that really makes me wonder, do I understand the way scientists of the past thought at all? But in any case, again, for the instruments of the time, Aristarchus did a bang-up job here. And you could say, although his number was off, even his better measurement, again, he measured the sun to be about 10 million miles away. It's really 100 million miles away. Well, that still establishes kind of a hierarchy to the distances in the solar system. From the Earth to the moon, well, the Earth is about 8,000 miles in diameter. From the Earth to the moon is about 250,000 miles. And now they knew the sun is very definitively a lot farther than that. So the Earth-Moon system would be kind of a small, compact, cozy little thing compared to the distance from the Earth to the sun. So that relative kind of hierarchy of scales, that made sense. And even if the number itself was wrong, it's kind of good that they had a convincing measurement to say, okay, the sun is a lot farther away than the moon is. We can set up this the set of scales correctly. Now, as long as we are on the topic of this set of relative sizes, we were talking before about how if you're trying to measure both the size of an object and the distance to an object, that there are three big questions that you could ask yourself. How big is the object really? How big does the object look to me in my field of vision? How many angles of arc does it take up? How many degrees of arc does it take up is one way of putting that. And how far away is the object? And we said if you can measure the answer to any two of these questions, then you can calculate the answer to the third one. Now, Aristarchus at this point had, for the object being the sun, he had measured the distance to the sun. He got about 10 million miles. He already knew the apparent size of the sun in the sky. How many degrees of arc the sun takes up in the sky. Again, that was that Calvin's Dad cartoon. Do this when the sun's setting, and you can look to the sun without. The software, again, is like making all these little emojis and stuff. It returned my thumbs up gesture there. I guess the software approves. If you hold your thumbnail up against the disk of the setting sun, and again, I say the setting sun or the rising sun because those are the times that you can look at it without danger of eye damage. The sun's disk is about half the width of your thumbnail, which means it's about half of 1 degree of arc. This was already known, so they knew the answer to one of those questions: how big does the sun look in the sky? Aristarchus had now answered a second of those big questions: how big is the sun really? Or I'm sorry, how far away is the sun really? He got 10 million miles. From that, he could calculate the size of the sun. What he got for the size of the sun was about 100,000 miles in diameter. Now, because he had the wrong number for the distance, that means he also was now getting the wrong number for the size. The sun is not really about 100,000 miles in diameter. It's more like 1 million miles in diameter. If you say that's different than the number you gave us just a moment ago, we're talking about two different measurements. The diameter of the sun, the size of the sun, is about 1 million miles. The distance to the sun is about 100 million miles. Now, again, you could say, well, so why is this an impressive measurement? He got the size wrong. But again, the kind of hierarchy of relative scales makes sense. Whether you go with his incorrect number or with the correct number that we know now, you would either way, you would conclude that the sun is a hell of a lot bigger than the Earth. The Earth is about 8,000 miles in diameter. The sun is about 1 million miles in diameter. You could swallow so many Earths within that celestial body that is the sun. In fact, in real life, you could actually take this whole Earth-Moon system, this is 250,000 miles, this is another 250,000 miles, so the diameter of the moon's orbit is 500,000 miles. You could take that whole system and you could place it inside the sun, and it wouldn't overlap out the edges. So again, Aristarchus' number was not perfect, but it was establishing a hierarchy of scales that kind of give you a good idea how big certain things are. Is there anything else I want to say about this measurement? Probably, but nothing that comes to mind at the moment. So I'm going to kill this recording, and I will see you all in class this week. Have fun. Take care.